All right, so you guys fairly familiar, comfortable with the dot product, right? Well, here's what we're going to do today. We're going to do the dot product, as Shakespeare would say, by another name, right? But it's still a rose, baby. This is called inner products. All right. How many of you have ever heard of this? Yeah, if you haven't, you will. In fact, you will right now. Definition. Let me be an inner product of B is a function that inputs two vectors and outputs a real number. So my notation will be like so this is the function. It's just this funny bracket thing. This is the notation I use for inner product. You input two vectors, and what does it give you? It spits out a number. And this well, that didn't go so well for me today, did it? So the output will be a number, and it follows the rules of the dot product in the following sense. So not just any function. One, so sometimes we say the function is symmetric. It doesn't matter what order you take this inner product in. Number two, so it spreads out. The dot product does this too. If you have u plus v dotted with w, it's u dotted with w plus v dotted with w. So we're just mimicking. This is often what happens in math and how people make leap further. Is you take something that works very well, like the dot product, say, how can I stretch this out and make it more all-encompassing? It plays well with scalars. And let me say this for all vectors u, v, w, and v, and scalars numbers and r. 3 lambda u, v with lambda u, v. By the way, by the first rule, this also works in the second coordinate because you can turn these around, you can slip that in and turn it back around, and you could also put the lambda in the second coordinate, right? And 4, anybody remember what the last, this is kind of one of the most important rules of the dot product that allowed us to do so much stuff with it. Anybody remember what it is? What happens if you dot a vector with itself? That's right, you get a number that's greater than or equal to 0. So I want to mimic that here. When I take the inner product of a vector with itself, it gives me a real number that's greater than or equal to 0. And I also want inner product of itself is equal to 0 if and only if u is the 0 vector. So the only vector whose inner product with itself is 0 is the 0 vector. Okay, so how about some examples? So And we'll let it. Okay, there's the notation I'm going to use for my vectors. Let A and B be positive, and I do mean positive real numbers. Then I want to define the inner product of U and V as equal to A U1 V1 plus B U2 U2. Does anybody see what this is a special? This is a generalization of. What does this remind you of? If it weren't for the A and B there, so in particular, if A and B were both one, what would this look like? This is the ordinary dot product of A and B are one, correct? So this is kind of just a little stretchy different dot product, right? I challenge you to verify all this, right? It's clear that it doesn't matter what order it's in, because all that does is turn the U's and the V's around and you get the same numbers, right? Checking this is the same thing as the dot product. It's not hard but obnoxious. Pulling constants out is easy too. And let's look at the fourth one. That's always the most interesting one. What happens if you have U dot U? Or not dot, inner product of U. This becomes A U1 squared Everybody agree with that? Somebody explain to me why this is greater than or equal to 0.
Well, A and B are greater than 0.
That's the important. So certainly these two are positive, greater than or equal to 0, right? And so if this is positive, and by positive, I mean this is truly positive, and this is positive at least 0, then this is greater than or equal to 0. Right? And because A and B are positive, what has to happen for this to equal 0? What must happen? So you're allowed to vary U1 and U2, but A and B are positive and stuck. What do you have to do to U1 and U2 to make that be 0? They both have to be 0. Everybody agree with that? And so that's why you got this. The only way this turns out to be 0 is if U is 0. Okay. Okay, there's one example of an inner product. And like I said, if A and B are both 1, this is the ordinary dot product you're used to. Let me give you one that's a little bit more exotic. And actually, I'll ask where we might go from there. Let's look at yeah, I'll do it. Y'all remember this one of my favorite vector spaces. This is the vector space of all polynomials of degree n or less. Okay, careful, almost trick question. Anybody remember what the dimension of this vector space is? Good, it's n plus 1, right? Because the basis, a basis is 1x all the way up to xn, so you got n plus 1. Check out this kind of cool inner product. So these are, oh, and let me do this here. Let T0, T1, all the way up to Tn be n plus 1 fixed numbers, fixed real numbers. So I'm going to define the inner product of P of x, Q of x, to be this. So what I did, basically, here's what I do. Take every one of these fixed numbers, they're always the same, these are. Plug in T0 to both P and Q, multiply together. Take T1, plug it into P and Q, multiply them together. All the way up to take Tn, plug it into P, plug it into Q, multiply them together, then add the whole shebang up. Okay. Let's take a quick gander at this. I'm not gonna go through the careful proof, but does it matter what order? No, because the number PT0, QT0 is the same as multiplying the numbers the other direction, right? No problemo. This one's a little bit harder to verify, but it's, again, it's polynomial multiplication. This works as well. And so does this. What about this one? I do want to check out that last one. What happens when I do this? Inner product of the cell, I get P0 squared plus P1 squared plus P2 squared. And what can you say about this?
It'll be positive.
Certainly greater than that. Right, because what are you doing? You're adding up a whole bunch of square numbers, right? So, everybody okay with it? Now, this one's a little bit more tricky. Notice the zero vector here is the zero polynomial, right? It's the polynomial, all of whose coefficient is zero. What happens when I plug in any number to the zero polynomial? Any number gives you zero. Everybody agree with that? Because I mean, it's just the function y equals zero. Plug in any number to that and you get y equals zero, right? The interesting part is the other direction. Suppose that the inner product of P with itself is zero. I need to conclude that this polynomial is zero. Well, this means that P of T0 squared plus P1 squared plus P2n squared is zero. Now, for that, can somebody tell me what is necessary for that to happen?
All the T's have to be zero.
All of the, so you're squaring a whole bunch of numbers and getting zero. That means none of these can be not zero, because otherwise you're going to be bigger than zero. So you have to have P of T0, P of T1, P of Tn, all zero. That must happen. Everybody agree with that? Can somebody tell me a conclusion you can come to? Well, so let me ask you this. So you may not be able to find them, but how many roots does a quadratic polynomial have? Two, right? And it could be the same two roots, right? How many roots does a cubic polynomial have? How many roots does a 14th degree polynomial have? 14 complex roots. How many roots does this polynomial have? Uh-oh. This has n plus 1 roots. It has one more root than the highest degree it could be. How can this happen? Right, because isn't it true that a polynomial of degree n can have at most n roots? This polynomial has n plus 1 roots. I guess my only conclusion is this polynomial can't have a degree. And there's only one polynomial that has no degree. I know what it is. Zero. The zero polynomial. Only a zero polynomial. Roots. Because we said that the degree is at most n, this can only be a polynomial. So we've shown this last part. If the inner product is zero, it has to be the zero polynomial. So this is an honest to goodness bona fide inner product. And what do? Basically, we added values of the polynomial, right? We plugged in n plus one different points, multiplied together, added up. Anybody know what the next step to this might be? Anybody notice what this mimics? There's something that you probably encountered in calculus that comes from a sum. Maybe a sum and a limit. This should have really been integrated into your education. So we're going to see the continuous generalizations of this in a moment. Okay, any questions so far? Okay, so this is what an inner product space is. These are basically the properties of the dot product. They mimic the dot product. This last one is perhaps, arguably, the sexiest one of them all, because it allows us to do a little bit of geometry, right? This last one allows us to talk about things like length and angle and so forth. So, let me give you a definition. A vector space equipped with an inner product is called, drum roll please, an inner product space. So it's like a vector space, only it's got this extra structure to it. It's got this extra inner product on it. Every vector space we do in this class, we can equip with an inner product. Okay, so in an inner product space, you can find length, and you do it the same way that you do with a dot product. Hey, if you want to measure the length of a vector, take the inner product with itself. And I don't know much, but I do know that this gives you a number. And this number is greater than or equal to 0. And what can I do to a number that's greater than or equal to 0? I can take the square root. So we can define the length. We can define other things that we've defined before. A unit vector is one of length 1. So we can use that length and scale it to whatever you like. 3, the distance between two vectors is length of u minus v. The two vectors being v as before. We can define the angle between two vectors. using the inner product. And we can also define two vectors are orthogonal. That is with respect to this inner product, if root product. If the inner product is 0. So, 6 you got all this stuff, you can even do the Gram-Schmidt process in this more general setting to have a orthonormal or orthogonal basis, whatever you like. And I'll do an example of that probably at the end with kind of a fancy inner product space. But let's look at the P2 X. And we'll let T0 equals and I'm gonna be give me 3 numbers and make it easy because I've got a pea-sized little brain. I'll ask, is there 3 different and simple?
3, 2, and 4.
Okay, more for that. Okay, suppose we're doing the exact same example we did with P and X. These are my 3 points I'm going to plug in. Find length. Let me make up some polynomial. Let's find the length of the polynomial, right? Length with respect to the center product. Well, let's take the inner product with itself, and that should give me the square of the length. This should be P of 1. Oh, I'm sorry, not 1. P of 3 squared plus P of 2 squared plus P of 4. Right. So let's see. What's P of 3? It looks like 9, 12, 13. P of 2 is 4, 6, 7. And P of 4 is 21. Right, okay? So this is like 169 plus 49 plus 441. And let's see, those two come to 610. So this looks like 659. I reckon. And so the length of the polynomial 1 plus x squared in the center product space is the square root of 659. Right, okay, I might ask myself something really wacky, like oh, well, I'm not quite sure what that means, right? Because I can't really draw a good picture of it, but I do have a notion of angle, and I do have a notion of orthogonality. Let's find the angle between this. Well, cosine theta is the inner product of x squared and x plus 2 over the length of x squared. Length of x plus 2. Right? So I reckon that we've got some stuff to figure out here. So the inner product of x and x plus 2 is p of, let's see, what did you give me? 3, 2, 4. P of 3, q of 3, plus p of 2, q of 2, plus p of 4, q of 4. That's the inner product. So this is going to be, let's see, that's going to be 9 times 5 plus 4 times 4 plus 16 times 6. So this turns out to be 96 and 16 is 112 and 45 is 157. And we need the length of x squared. Well, actually, let me do it this way. X squared in the product of x squared is p3 squared plus p2 squared plus p4 squared, which equals, in this case, let's see, that's going to be, when I put in 3, it's going to be 9 squared is 81. When I plug in 2 to x squared, I'm going to get 4 squared again 16. Yeah, these are all 4 powers. And so when I put in 4, I'm going to get 16 squared, which is 256. Let's see, that's 97. So that's 8. So the length of x squared and finally, the inner product here is q of 3 squared plus q 2 squared plus q 4 squared, which in this case, when I plug in 3 here, I get 5, so I get 5 squared. When I plug in 2 here, I get 4, so I get 4 squared. And when I plug in 4 here, I get 6, so I get 6 squared, which is 36. So that's 77. So length of so in this particular inner product space, the angle between x squared and x plus 2 is going to be 157 over the square root of 353 square root of 77. Okay. Okay, any questions? I'm going to do one more fancy example, but first I'm going to give you 2. These are kind of big results about inner product spaces. One of them is called Cauchy-Schwarz inequality, and the other one is nothing that's too surprising because you've probably known it for a while, and that's the triangle inequality. How many of you have heard of the triangle inequality? Basically what it says, you've probably heard this at least as folklore in the geometry class. If you have a triangle, then any two sides, take the length of any two sides and add them up, it's longer than or equal to the length of the third side, right? So that's an old chestnut that we'll get out of this. So, this is called the Cauchy force inequality. If U, V, or elements of V, and here I have the inner product space. So it's vector space and it's got this inner product. Then the length. Well, the inner product of U and V is some number, positive or negative. When I take its absolute value, I get a number, and that number is less than or equal to the length of U times the length of V. So the size of the inner product is no more than less than or equal to the product of the lengths of the two vectors involved. So I'm gonna prove this very quickly, as with the triangle inequality. Proof. If U equals 0, then it works. Okay, that's a bit of silliness, but let me explain this. If U equals 0, if U is a 0 vector, then the length of U is 0, so this side is 0. And if U is 0, then the inner product of U and V is 0. So you get 0 is less than 0, no problem. So U being 0 is no problem, and you're going to see why I did that as a separate case, because I'm going to project on you. If U is not equal to 0, then the projection on U of V on U is, if you remember this, just like with the dot product, this is V and the product U. Now I'm going to appeal to Pythagoras a little bit. This isn't the special case of triangle inequality. If you remember, the projection of V on U is this yellow vector. It's in the direction of U, or it's, I should say parallel to U, right? And it's V's projection down there. Everybody remember that? Notice that because even though I don't have a full triangle inequality, I do remember that the hypotenuse of the triangle is greater than or is the longest side of the triangle in a right triangle. Everybody okay with that? So this yellow is smaller than or equal to the length of V. Everybody okay with it? So let's finish this off. Let's take advantage of that observation. So the length of this is the absolute value of VU, because this thing right here can be positive or negative. This thing right here, I'm going to rewrite as the length of U squared. And here, because remember, I'm taking the length of this, and so it's this number here times this. And this is less than or equal to the length of V, just like we said here. Now, this cancels down to one factor. And if I take this over to the other side, I get what I want. Any questions? And one more, before we do the fun example, the triangle inequality. Triangle inequality. V is an inner product space. Then the length of U plus V is less than or equal to the length of U plus the length of V. So think of this as three sides of your triangle, U and V, and U plus V is is the third side, I should say, not necessarily a hypotenuse. The length of any two of the sides is greater than or equal to the length of the third one. So this uses the Cauchy-Schwarz inequality that we just had. The length of U plus V squared is U plus V, inner product with U plus V. And if you multiply this out, using properties of the inner product, this is U, 2 UV plus VV. Just break this apart in pieces. This is inner product U and U plus V, U plus V, and then break apart the second piece, and you get this. This is the length of U squared. This is 2 UV length of V squared, right? And you know what? This can be either positive or negative, can it? Because it's an inner product, right? So let me do this and make this positive. Right? Everybody okay with me? So now it's positive. Notice that this, by the Schwarz inequality, is less than or equal to length of U squared plus 2 length of U, length of V, plus length of V squared. Because this thing is smaller than this thing by the Schwarz inequality. And this is the length of U plus the length of V. 1 squared. Square that, and 2 times the product in the middle. So you have this squared is less than or equal to this squared. If you take the square root of both sides, you get the length of U plus V is less than or equal to the length of U plus the length of V. And there you have it. Okay. Any questions on that? I've got some time to develop this example here. Did everybody kind of get that example of the inner product where I took the two polynomials and plugged in numbers? You got how those computations work? What's the next step up from adding stuff? Let me give you a nice inner product space. And this one's actually easier to verify as an inner product space than the other one. What did I end up doing? Step one thing. These are all continuous functions defined on the interval from -1 to 1. So this could be anything you want, e to the x, cosine x, natural log of x minus 2, right? Because that's continuous everywhere on that interval. I should say absolute value of x minus 2. What else? 1 over x squared plus 1, anything you like, right? There's an inner product. That's the next step up from adding stuff. You just kind of add everything into it, right? In a certain sense. Okay. I'm going to show some of the details to this a little bit more carefully. Why is it an inner product? One, certainly it doesn't matter what order you put the functions in, right? I agree with you. What else do we need? Well, 2 f of x plus h of x, say, comma g of x. Well, this is equal to the interval of f of x plus h of x and g of x minus 1 1. And what can I do to this thing? Well, this is the integral minus 1 1 of f of x g of x plus f plus h of x g of x. And what's the big thing you can do with an integral like that? You can split it up into 2 different chunks. You can split it up into both chunks if both pieces are integrable, but since the functions are continuous here, everything's integrable. So I've got complete freedom here. And this is f of x, g of x, plus h of x, g of x. I'll let you do the third one for the scalar. You can pull out the scalar, but can you pull constants out of integrals? You betcha, right? So that's going to work as well. So I'm getting all excited about this. So how about the last one? Well, I bet you all learned in calculus that if you integrate a function that's not negative, you get an answer that's not negative, right? So this is greater than or equal to the integral from -1 to 1, 0, right? Because this thing can never be negative, which is 0. So your inner product with itself is greater than or equal to 0. All right. I think it's pretty clear that if f of x is 0, then you integrate it and get 0. Here's the trickiest part of this. Suppose the inner product f of x with itself is 0. Suppose that, just for giggles. Then this means the integral from -1 to 1 f of x squared dx is 0. Now I'm gonna really wave my hands at this. I'm not gonna do a careful treatment unless you're excited about this, and you can come by my office and I'll be happy to talk about this. You may regret it, but I'll be happy to talk about this afternoon. So I know this integral is 0, correct? I claim f of x naught is 0 for all x naught between 0 and 1. And that will mean that f of x is the 0 function, right? What happens if it's not? Would everybody agree that f of x, anything I draw for f of x is going to be above this axis, right? Because it's got to be not 0. Suppose it's some x naught. It's not 0. That means it has to be a little bit bigger than 1, right? Would everybody agree that there is some neighborhood? This is why the delta epsilon stuff you did in calculus, or maybe not, is important. There is some neighborhood around here where you don't get to 0, right? You can make this small enough to where you've got a little bit above. You can't go all the way down to 0, right? Everybody agree with that? This is because the function's continuous, right? You can't just go from here down to here, right? Because of it's continuous, there's a small enough interval around here, so this is still above the axis, right? Let's call this x naught minus delta, x naught plus delta. And in this interval, the function is positive. Agreed? So the interval from x naught minus delta to x0 plus delta of f of x squared dx is greater than 0. And so since the interval from here to here is 0, is positive, the interval all the way from here to here has to be positive because it can never be negative, right? So that's essentially it. So if you're ever above the axis here, then your integral can't be 0. So that means that if the inner product is 0, then f of x is the 0 function. Everybody okay with that? So I'm going to leave you for a challenge. And we'll probably come back because we've got some extra days in the syllabus. But I'm going to leave you this for now. So take v f from -1 to 1 into r f continuous. So here's my little challenge problem. So notice P2x is inside of here, right? Because these are all argument functions. Use the Gram-Schmidt process. The inner product FG equals the integral FG dx to find an orthonormal basis. Let's call this W. Or let me tell you what I got, and you can check me, make sure that I didn't do this wrong. I got, what did I get? I got 1x, so the first two are the same. How about that for luck? And I think I got x squared minus 1/3. See if you get that, and then go crazy, right? Try the same thing for, instead of this, do cosine x, cosine 2x, cosine 3x. See what you get. And actually, this isn't just me torturing you, because this technique, this particular inner product, is very important in Fourier analysis, which a lot of you have coming up. Okay, any questions? All right, y'all put that in your pipe and smoke it, and we will see you on Friday.